Okay, here's lesson number 4, and this is all about the uncertainty principle. Heisenberg is the man we have to thank for all of this interesting stuff that's about to follow. Really, light and other tiny particles um, are tiny, teeny, teeny, tiny, and they're invisible to us humans, to the naked eye. Really, even they're invisible to us on smaller scales as well. We can't directly observe an electron or a proton or a neutron. Okay, so really, because we can't observe what they're doing, we have to rely on probability in order to describe their motion. So, as you'll find out if you take courses in quantum mechanics, even at, say the first year level or the second year level in university, you'd find that probability is a very, very important concept in quantum mechanics. So let's illustrate this importance. Just illustrate it as we look at Young's experiment once again. Okay, so here is the setup that we had when we looked at Young's experiment. We've got two slits that are separated by a distance d, and they make a maximum over here at this point on the screen. Okay, and so basically we've got a single source of photons. We're going to fire photons at the slit, and what we're going to observe is when the photons are emitted one at a time, we can ask the question, okay, so if we emit photons one at a time, do we see an interference pattern? And we showed a little video in class, Dr. Quantum, when he looked at the double slit experiment. And of course, the answer to this, if you remember, do we see an interference pattern, is of course yes, we do see an interference pattern. And it looks something like the image in your note just below. Even though photons are emitted one by one, had nothing to interfere with, they still form an interference pattern. And so the question is, why does that happen? How does a photon know to create, how do these individual photons know how to create this interference pattern on the wall? And this is what's important. The answer is, it's not that we don't know, it's that we can't know. Okay, so we can't know where a photon goes. We can't know if it goes through the first slit, or if it goes through the second slit, or if it goes through both slits, or if it goes through neither. We can't know where it goes because what we'd use to measure would, of course, be light, right? We'd use other photons to measure where it went. We'd look, we'd peek. But photons will interact with other photons. So essentially what we do when we measure an experiment like this is that we actually interfere with what's going on, and we force the photon to take a position. So the concept known as determinacy says basically when we're measuring something, when what we're measuring is comparable in size to what we're attempting to measure with, we have difficulty coming to any solid answers. So here's a thought experiment. Let's say we want to measure the location of a boat that's floating along in the ocean. And we use light waves to locate that boat, right? No problem. Light is a lot smaller than the boat. And yes, light would interact with the boat, but it doesn't have enough energy to mess up its location. However, if we used a different type of wave to measure the boat's location, let's say we used water waves to measure the boat's location, basically we would affect the experiment just by measuring. Right? If we used water waves to kind of say, okay, let's go and see, and we'll see if they bounce back, we'll kind of try and locate it that way. Well, our water waves would actually push the boat away because they would interfere with the boat itself. So we obviously can't use water waves because they're large waves and comparable in size to what we're trying to measure, which is where the boat is. The accuracy of any measurement depends on how much the measuring instrument interferes with the object being measured. Okay, so that's from your textbook, and that kind of enters into this world of Heisenberg's uncertainty principles. So because of determinacy, we can't observe what happens in between the slits and in between the screen. So we don't know what's going on in there. So we can only look at the screen and predict the probability of where photons will end up. Okay? So Heisenberg basically said that, Okay, let's consider a simple model of single slit diffraction. Okay, so here's our diffraction pattern, and here's some photon, and it zips through this opening, right, with some momentum px, right? And this opening, we don't really know where it goes through. We've got some uncertainty in here. We don't really know how much momentum it has, but it's got some. It's got some px and py, and because it zips through here and this slit is pretty small, this photon's going to kick off part of this slit. So it might ricochet off here, it might ricochet off here, because this slit is really, really tiny. So it's going to interact with the particles in the slit, and it's going to pick up some momentum in the y direction. So basically, the midpoint here is the central maximum. Photons have momentum, and they will interact with other particles. So let's take a look at when this photon interacts with the particles in the slit, what happens to it. All right, so here we go. They're deflected, so they pick up a little bit of momentum in the y direction. Here's our momentum vector, px and py, and we can represent that as mass times vx, vy. We know that the magnitude of the momentum is the square root of the x component squared plus the y component squared. And we also know that the angle that this vector is traveling along is py over px, and the inverse tan of that. So we know the angle that it's going on, we know the magnitude that it's traveling at. Everything's defined as this vector is up here. Okay, so but theta is very, very small because we're talking about very small angles. And you'll remember we made a small angle approximation when we looked at deriving diffraction and Young's modulus, Young's double slit experiment. So theta is approximately equal to tan theta for really small angles. So we can say, oh, well then in this case, theta is just equal to py over px. We'll call that equation number 1. We'll put it inside of this little dotted box here because this is not a final equation yet. This is just one that's going to help us along the way. Now for a single slit, we know that the first minimum occurs at m lambda, where m is equal to 1. So that's the first minimum, because we're only interested in the central maximum at this point. And so basically for the first minimum and for small theta, because small angles of theta, sine theta is approximately equal to theta as well, we get lambda equals w theta 1. And this is equation number 2. And we'll put this inside of a dotted box because, again, this is not the end. This is just kind of helping us along the way. All right, so let's use those two results. And, of course, we'll set them equal to each other. And what we arrive at is, okay, well, we knew what the initial momentum of that photon was. It's just h divided by its wavelength. So if we know the wavelength of the photons that we're using, which is easy to do, then we know the initial momentum of those photons. So hey, we actually know what px is. So we can sub this in here, and we can say, okay, so py times lambda over h equals lambda over w. So look at these two lambdas. They're going to cancel out because they're the same thing. And we get that py is approximately equal to h over the width of the slit. But because this is uncertain, we don't really know how certain this is, we can say, hey, we're uncertain about the position of this photon in the slit. Like we're not, because it's so tiny, we don't really know where it left. So we don't really know much about its momentum. We're uncertain. And so we'll call this, instead of writing this as the momentum in the y direction, we'll write it as the uncertainty in the y dimension. There's got to be a little bit of a range here, and so we'll use delta py. Because we don't know where the photon was released, we can call this w, this slit width, delta y, because we don't really know where in the slit it was released. It was released in there somewhere. And so if we put this together and we change our constant to h bar, we get that the uncertainty in the momentum times the uncertainty in the position is always greater than or equal to this constant h bar, which is simply h divided by 2 pi. Okay, it's another constant. So what does this all mean? Well, we'll talk about that in one moment. We can also quickly just apply this to energy as well if we use the ideas of Planck and de Broglie. And we say, okay, well, if here's our uncertainty principle, but we know that h is equal to E over c times lambda, right? This is just our energy equation rearranged. Then we can kind of pop this in here. And we know that lambda over c is equal to delta t. Basically, v equals f lambda. Then this is what we get. We get that delta E times delta T is approximately equal to delta P times delta Y. And hey, we said initially that that was H. So we can rearrange and then rewrite our uncertainty principle as, hey, the change in energy times the uncertainty in the energy of a particle times the uncertainty in the time the particle has that energy is always greater than or equal to h bar. So here it is. This is the uncertainty principle. If we know the position of a particle precisely, then we can't know its momentum precisely, and vice versa. If we know its momentum precisely, we can't know its position. Similarly, if we know the energy of a particle precisely, we can't know the length of time it's had that energy, and vice versa. And so basically what you'll notice is that in these two equations is that, of course, if they're always greater than or equal to h bar, when one goes up, then that means the other has to go down, because they're always equal to a constant. So why isn't this observed with macroscopic objects? And that's a question that you should ponder. Why don't we have to worry about Heisenberg's uncertainty principle? Why is it that right now you could go outside and you could say, okay, there's a car driving by my window. I could tell you the position and I could tell you the momentum of that car right now, both with a great deal of certainty. How come we do not apply this to macroscopic objects? So think about that question, because that's one to ponder, and then we can talk more about it in a few moments. Here's an example. In a diffraction pattern, an electron is deflected, and the uncertainty in its speed is 1,000 meters per second in the y direction. How precisely do we know its position in the slit? Well, we know what h bar is. It's just a constant. We know the mass of an electron, and we know the uncertainty in the electron speed. Okay, so P, the uncertainty in its momentum times the uncertainty in its position, this is what we're trying to find, is always greater than or equal to h bar. And we know that the uncertainty in the momentum is given by mass times the uncertainty in the speed. So we can put all this together, rearrange for delta y, and we can divide. And here it is with our numbers subbed in, and we get 0.11 micrometers. Now, you may be thinking, oh, this actually is a pretty small number, right? 0.11 micrometers. Well, is that precise when you compare it to an electron? Think about how tiny an electron is. 0.11 micrometers is actually quite a bit larger than an electron, and so this is actually not a very precise answer. Example number 2, very similar. An alpha particle is emitted from the decay of uranium-238. If this particle has an uncertainty in its energy of 34 kiloelectron volts, what's the uncertainty in its position? So this one, we're talking about energy, but I'm asking you about position. So it's likely that we're going to have to do some figuring out here. So 34 kiloelectron volts, basically we can convert that into joules, because if we're going to work with H and H bar, we need to be in metric units. A mass of an alpha particle is, of course, it's two protons and 2 neutrons. So we've got the mass of 2 protons plus the mass of 2 neutrons, which turns out to be 6.7 times 10 to the negative 27 kilograms. How fast is it traveling? Okay, well, we know its energy. So if we know its energy, we can zip this in here, and we can say, oh, well, let's just solve for v. And it turns out it's 1.27 times 10 to the 6th meters per second. Okay, so now that I know v and I know mass, I can use my uncertainty principle to calculate its momentum. This is, of course, the uncertainty in its momentum. And it's about 8.5 times 10 to the negative 21 kilogram meters per second. Apply this in the uncertainty principle, rearrange, and I solve for y, which is greater than or equal to 1.24 times 10 to the minus 14 meters. And that basically is how we do calculations with the uncertainty principle. It's very, very simplified, and the concepts are pretty confusing. However, these are some straightforward examples, and we'll have more opportunity to talk about this in class. We'll just end off this part of the unit by talking about some developments in quantum mechanics that go kind of beyond where we are now. And it gets very complex from this point out. It becomes more dependent on calculus and some involved mathematics. And so we end our look at this kind of subject area here. Right? So the next stages, though, in quantum mechanics really have a lot to do with describing tiny objects as waves. Okay, so of course de Broglie illustrated that, hey, everything can be described as a wave. We can give it an associated wavelength, and so some of these things, basically matter waves, are described by wave functions, which involve complex numbers and a whole bunch of other interesting terminology. Wave functions contain all the information that we need to know about the particle, and it's very related to the probability of finding a particle at a specific point in time in a specific spot. So the wave function for de Broglie basically must satisfy this thing called the Schrodinger equation, which is listed below. And one very common thing that you'd see in university courses in quantum mechanics is to determine a solution for the Schrodinger equation, and then determine the allowed wave functions and all the energy levels for the system in question, and so on and so forth. And it gets pretty tricky after this. This is, of course, all calculus here. These are partial derivatives, and you don't need to worry about this for our high school course, but it's very interesting. And many people, of course, when they hear about quantum mechanics, they've heard about the Schrodinger equation. And so here it is presented just for observational effect, and not much more. And so that is our very brief 4-lesson look at quantum mechanics.